Greetings! In today's lesson, we're going to be talking about artificial intelligence as it's applied to games. We're going to be talking about how an AI goes through the sense, think, and act cycles, and then we're going to show you how you can develop some very simple AIs to play games. So in this lesson, we're going to be talking about the sense, think, and act cycle, which we're going to use as the general framework for developing AIs that can detect what's going on in their environments, decide what they're going to do, and actually carry out that action in the game world. We're also going to introduce techniques like decision trees, finite state machines, and search trees, and show you how AIs use them during the thinking process to make effective decisions. We're going to go over a lot of comp sci terms, so game state, heuristic, depth first, breadth first search. We're going to show you how they're all used by AI, and finally, we're going to develop some very simple rule-based AIs to play some games. So I'm really excited to talk about AI in video games because it's probably one of the most natural and obvious fits for the technology. AI is all over video games. If you're playing a real-time strategy game and you're trying to get your army over this hill, AI is actually being used to navigate the paths for each individual units as it goes from A to B. But we see AI all over video games, whether it's to control the player's character, control allies, or maybe like non-playable characters. If you're playing a game like chess or checkers or something, AI could be the player's opponent. It could be like an enemy or a boss that you have to fight. So here, for example, is a clip from the game Super Mario 3D World for the Wii U. This is my son's favorite game, and you know that the player's controlling Mario, and all he has to do is go up the tower, and if there wasn't any AI, this would actually be a very boring game. But as you can see, with AI, we can add some challenge to the game and make it really hard for Mario to get to his destination. And the AI is going to throw, wow, look at that. The AI is going to throw everything under the roof at the player. And the challenge here is devising an AI that is challenging enough to make it hard for the player to reach their goal, but not so hard that that the player is never able to achieve it. So there's an interesting tension that developers have to think about when they're designing AI for games. So how do we actually create a game AI? To be clear, there's a lot more nuance to this than I can discuss in a brief lesson, but for the purpose of this class, we're going to talk about how game AIs make decisions using a three-step process, which we call sense, think, and act. The sense phase is basically where the AI agent is collecting all of the information it needs from the environment to make an informed decision. So maybe, for example, the AI needs to know the location of all the other players in the game, any power-ups, protective cover, maybe how much health the other players have, or how much health it has. Sensing in the real world is really difficult, so like when Tesla made their self-driving car, they had to put sensors all over their car in order to determine what was around them. In contrast, in games, sensing is typically pretty easy because we already have to keep track of where all the players are so we can draw them. So all that information is usually available to the AI. The next phase of Sense, Think, Act is the thinking phase, and this is where the AI is going to be spending its time looking at all the possible actions that it can perform and then trying to determine what the best one is. So for example, like in a Call of Duty game, maybe it needs to decide whether or not it's going to shoot or like try to duck or take cover. In chess, you can think of every possible move that the player could take during a particular turn and then evaluating them all to see which one is most likely to lead them to a victory condition. Finally, in the act phase, we carry out the action that the AI chose in the think phase. So here, this is where we actually attack or move or use an item. Once we have completed the act phase, the entire cycle repeats itself. The AI then takes another opportunity to sense its environment, it considers all the new actions available to it, and then it acts again. So by continuing this process over and over, the AI is able to react to the environment as it's changing around it. So now let's see all of these steps in action. If you go to the course website, you can download the Pong demo, and Pong is basically just a recreation of one of the earliest video games. It was originally produced as an electronic tennis game in university supercomputers, and eventually it got moved to the Atari where it became famous. So if you go and you download the file and you press play, you will basically see this, and yeah, you can actually control it. So if you press up and down on the arrows, you can control the blue player. And our goal for this exercise is going to be to go ahead and write an AI that can play as the red player. You'll notice the red player is not doing anything, so we get to win and have all that much fun. And okay, and yeah, sure. Okay, I'm done with that. All right, so now The version of Pong that we created does not contain any AI code, so you can just control the blue paddles. So now we're going to go through and apply sense, think, and act in order to figure out how we're going to control the red paddle. So in sense, we need to think about what information the AI needs to know. And at a minimum, the AI needs to know the location of the ball as well as the location of the AI paddle. Now, if you're trying to be advanced, you might want to know like the velocity of the ball. You might also want to know like where the opponent's paddle is, so you can try to steer the ball towards a corner he or she's not prepared to get. So sensing, like I said, is very easy in the code. Okay, the AI is doing much better than I'd anticipate. Okay, so you'll notice that there are tons of variables in this game, and one of the variables is this one here, which controls the location of the paddles, as well as these variables which contain the X and Y coordinates of the ball, as well as the velocity of the ball if we needed it. We won't for this example, but again, like I said, sensing is really easy because we already have these variables that we need so that we can draw it, right? In the think phase, this is where we're trying to determine what direction we want to move the paddle. And if you think about it, there's only really three options. If the ball is above the paddle, we should move up. If the ball is below the paddle, we should move down. And if the ball is right in front of the paddle, we shouldn't move at all, right? So we can actually go ahead and detect that. If you actually go into the code and you scroll down, you will first notice that this is basically a souped up version of the Python graphics template that we give you. You have the erase function, draw, update. There's this get inputs function, which is where we're going to get inputs from players. So if I scroll up, you will see that there are two functions that it calls. This one gets the human player's input, and here's where we're going to get the AI player's input. So you'll notice in here, for thinking, one of the things that I have provided as just an assistance is some variables that this is true. This variable here is true if the ball is above the paddle, and this one here is true if the ball is below the paddle. All right, and then in the act phase, we're actually going to make the paddle move. So we're going to call these two functions that I created that move the paddle for us. So let's actually just go ahead and do it. Like I said, all we really have to do is put a couple of if statements to build some logic. So for example, if the ball is above the paddle, right, if that's true, then we're going to go ahead and move the paddle up. And as a parameter, I just have to specify which paddle I'm moving, so I'm moving player 2's paddle. And then here, if the ball is below the paddle, then I'm going to go ahead and move the paddle down. So you should be able to see this in action. Notice I don't really need a condition for if the ball is directly in front of the paddle. That's just because if I don't put any condition for it, the paddle will do nothing, which is exactly what I wanted to do anyways. So let's press play. All right, and now you can see that even though it may not be, it's kind of behaving a little weird, but you already have a basic AI that can play the game of Pong. Notice how it's following where the ball is. So I don't think you can actually defeat this one because it's always following the location of the ball. So, you know, it's really on me to play a good game, but you can tell here I'm never going to win because it's always going to hit it. So this is a really effective AI, but I don't necessarily know if it would be fun. Alright. So now that we've seen a live example of sense, think, and act actually happening in a game, let's talk a little bit more about thinking. So thinking ends up being the most time-consuming part of the sense, think, act cycle, precisely because we have to think about all the possible things that the AI could potentially do, and then decide which one is the best. And the best is oftentimes a very nebulous and difficult to define term. There's a lot of techniques that you can use to think, but for this class I'm going to introduce three of them to you. Hard-coded rules, finite state machines, and search trees. So with hard-coded rules, we're trying to write down all of the specific things that an AI needs to think about, but to arrive at the best decision. So in Pong, we already did this. We wrote a set of if-then statements that controlled what we should do with the paddle based off the location of the ball. So another way that we could represent these if-then statements is using something called a decision tree. So given this code here, where we move the paddle up or down depending upon if the ball is above or below the paddle, we can construct an equivalent decision tree. So here we have two types of nodes. We have decision nodes, which represent points where the AI needs to decide what's going on, and then we have end nodes, which is a node that describes what the AI should actually do. So if it is the case that the ball is below the paddle, we move the paddle down. If it's the case that the ball is above the paddle, we move the paddle up. Otherwise, the ball is already in the range of the paddle, so we do nothing. So decision trees benefit from being really simple to write. That's why we showed them to you first, but they're not very scalable. For simple games like Pong, it's pretty easy to write a decision tree because there's not a lot of things you can really do. But in a game like a strategy game or a first-person shooter, or even if you're a Tesla and you're doing an automatic, driving car, there are a lot of decisions that you have to take into consideration to decide what the best thing to do is. And oftentimes there's so many rules that a human being can't articulate them all. There's just millions upon millions of rules. We just can't write them all in one place. So this technique is good for simple problems and it works quite well. But when you start dealing with more complicated problems, it's harder to come up with those rules from scratch. The next technique I want to talk about is the finite state machine. And finite state machines allow us to group AI behaviors into what we call states. So, for example, a video game monster might have two different states, a scouting state and an attacking state. So when it's scouting, it's looking for the enemy or the player, and then in the attacking phase, it's attacking the enemy or a player. So the idea here is that the AI, as it's sensing its environment, it's determining what state it should be in, and when it enters that state, it starts doing the behaviors associated with that state. So for example, in a game you might start off with scouting, and if the player gets too close, we transition to attacking, and then we start shooting at the player or whatever, and then when the player moves away, we return to the scouting state. So this is a very simple way to talk about changes in behavior of an AI based off of what's going on in the simulation or game. So here you can actually see a live demonstration of a finite state machine in action. This is the game Metal Gear Solid 5, and basically you play as a secret agent that's trying to infiltrate an enemy installation. And here you can see that the guard starts in this standing state, this idle state, until he hears a noise, and he transitions to a curious state. So now you can see him, he heard something, now he's trying to figure out what it is, so he's executing those behaviors. And now I'm not hiding very well. So now the AI switches over to a cautious phase, and what he's doing now, he's looking a little bit closer, he's going to approach, but it's going to be slowly, and eventually, when I'm seen by the guard, and I miss, okay, so I'm bad at this, the guard switches over to the alert phase, and in this state, it's going to start engaging and attacking the player. So you can see that even in modern games, this type of technique is readily used. Oh, that's cool. I actually did knock him out. Okay, but you can see how this technique is readily used to make very, it looks like complicated behaviors, but it's really just transitioning between these various states. The third and final technique we're going to talk about in this class is called the search tree. And a search tree is nothing more than a way for us to visualize all the possible decisions that an AI has to consider at a given point in time. So a search tree basically depicts two things. The first is the game state, and you could think of a game state as a snapshot of the game at a given point in time. So in a game of tic-tac-toe, a game state might be the layout of X's and O's on the board. It also depicts the possible actions that can be made from a state. So again, in tic-tac-toe, it might describe that you can place an X in this square, but not in this other one because it's already occupied. The idea is that during the thinking phase, the AI is going to start at an initial state and determine what actions are available, and sometimes it might look 2, 3, 4 moves ahead. The AI is then going to evaluate the state that the AI will arrive at as a result of taking an action. So it'll say, this action leads to a state, this action leads to another state, but this state is better than this other state, right? It picks the action that will lead to the best state, it takes that action, and then it starts all over again. So the idea here is that every time the AI is looking at its actions, it's trying to figure out which action will take it to the best next state. So rather than talk about this abstractly, let's apply search trees to a specific game. So here, if you go to the course website, you can download Spy Hunter, and make sure you grab all the files because it should be in a folder. And Spy Hunter is an old arcade game where you controlled a car, and the idea is that you are driving the car down the highway and you are trying to bob and weave between the traffic to get as far as you can without hitting the other cars. So Spy Hunter is normally a real-time game, but for the purposes of this discussion, we will treat it as if it is a turn-based game. So we can look at each step and what decisions the AI should be making. The yellow squares in this example represent all the places where a car can be located, either the player's car or an enemy car. And each turn, the player basically has three choices. Stay in the current lane, move to the left, or move to the right. Not all the moves are always available, but at most you have up to 3 choices. And finally, we're going to assume that the game is deterministic, and by that we're going to mean that we will know with 100% certainty what the game will look like if we decide to stay in the same lane, move left, or move right. And the way we're going to do this is we're going to assume that the yellow cars aren't moving and only the red car is bobbing between the highways. If we allowed the yellow cars to move with some probability, the game would be much harder. Alright, so if you go to the website and you get the code, you'll see, again, it's based off of our basic Python graph source code, and when you run it, you should see this. So you see the cars on the highway, and if you press the space bar, you can actually run it. So if you look at this function does not have any code in it to control the car, so when I press play, all you will see is the car moving forward until it eventually hits an opponent, and then the game is over. So what we're going to do is try to add and develop an AI so that the car doesn't do that, and instead it effectively goes through the traffic. So let's generate the search tree in order to see how we would use this technique to help us out. So here is what the highway looks like in our example, and we're going to look one move ahead. So we're just going to think about what is the next decision I need to make. So this is what the current state of the highway looks like to the car. And then we're going to decide, can I move left, can I stay in the current lane, or move to the right? So which decision should the AI choose? Well, obviously staying in the center lane is not a good idea, but moving left or right seems to be okay. So, okay, we can implement this pretty easily, right? We can make a decision that if what's ahead of you is blocked, and then moving to the right or to the left will get you to a non-block state, then that's okay. We should do that. So I'm going to go ahead and copy and paste the code and explain it real quick. So this is basically saying, if the road at the 1 minus where you currently are, so 1 row ahead, is blank, then do nothing. So this is the if the road's clear ahead, do nothing. This one is if you can move to the right and the road to the right of you is blank, go ahead and move right, and this is the same thing for left. Alright, so if I was to press play at this point, what you would see is the car would continue to drive straight because this rule is in effect, that it's just blank ahead. And then at this point, as soon as it's blank, it's crowded, it moves to the right. It's going to do the same thing, except this time it can't move to the right because you're at the edge of the highway, so now it moves to the left. And if we were to let the car continue to do its thing over an extended period of time, what you would see is that the car does demonstrate, it looks intelligent, right? It's swerving through the traffic. But it can still get pretty easily fooled. This is an interesting case, right? Once it gets here, it's the car, it can't go ahead because it'll hit a car. So then the next thing it'll do is look right and say, oh, it's blank ahead, and then it will get in, right? So it's pretty easy to fool this algorithm because it's only looking 1 move ahead. The same thing is happening in our example. If I move to, it looks right here, like left and right are valid decisions, but if I move to the left, I'm eventually going to get boxed in. So how do we avoid that? The easiest way is just to look more than 1 move ahead, right? So I could do the same thing I did last time. I can generate all the possible states from my current state, but then I could do it 1 more time. And again, because the game is deterministic, I am able to predict what the future will look like. So, if I move to the left, my only choice is to stay in this lane, right? The same thing happens if I move to the right. I'm here, I'll end up, all I can do is really stay in the same lane. And obviously there's nothing I can do in the center because the game's already over. So if I was to look at this choice right here, I would see pretty quickly that going to the left up here is an okay decision if I only look 1 move ahead, but 2 moves ahead is a bad idea. But moving to the right is at least safe for 2 moves. So this type of search, where we are looking at the decision tree layer by layer, 1 move ahead, then 2 moves ahead, this is what we would call a breadth first search. We're exploring the breadth of a layer before moving on to the next one. The problem, though, with this, what we're doing right now, is that clearly, we're safe 2 moves ahead, but I'm sure you can imagine a situation where it would be problematic if we only looked 2 moves ahead. In fact, what's the worst case scenario look like? Well, what if the road looks something like this, where it's safe 1 move, 2 moves, 3 moves, but all the way up to 7 moves before we realize that moving to the left is a really bad decision. In order to prevent ourselves from getting boxed in like this, we need to look as far into the future as possible. So, what we could do is take our search tree and expand it so that we can look at all possible decisions in the game and all the possible game states given what we know at the moment. So here's what the tree looks like. You're welcome. Right? It's fairly complicated, but it shows you basically the same thing. We just took the game and we naturally extended it. What would it look 3 moves out, 4 moves, 5, 6, 7 moves out, right? And now we're going to analyze it using, we can use the same methods, right? We can still do the breadth first, where we look at all of 1 move, 2, 3, 4, 5, 6, 7. Alternatively, and if we were to do that, it would be ABC. Notice I've lettered them here. So ABC, then DE, right? And it goes on. This is basically alphabetical order. Another way that we could look at the tree is using what's called the depth first search. And with depth first, what we would do is we make a decision and see how far down the tree we could go. Right? And we keep doing it until we examine all the paths. So for example, here we would look at A, then D, then F. Here we'd look at B. And then here we would look at C, E, G, I, L, N, P. And then if we once there's no more states after this, so we'd go back up, and now we go here. So we'd look at all possible combinations. It's important to remember that both of these methodologies will get you all the way through the tree. For this particular game, though, it's pretty effective to use a depth first search, because what we can do is we can just search through the tree until we find one that goes as far as we can, and in this case 7 moves ahead. And we just pick the first path that'll take us there. And if we do that, we will always find at least a path that gets us through the highway, and we won't run into the risk of being boxed in. So we can actually implement this type of depth first search. So I'm going to show you how I do that. So for this one, I don't have the power of copy and paste anymore. I wrote a function that calculates the depth first search for you, so you can already see it. And then it generates the longest path that it found. And what we'll do is, if the longest path, this is return, actually, I can go ahead and show you, it will print out if I do this. If I do this, it will print out, when I play the game, it prints out what's the path. And it actually will show you also that the longest path is to go left, and then go right, and you can see the path through here. So what I can do here is I can say, if the longest path, if the first node is less than my current player X, then I'm going to move the player left. And then I'm going to do the same thing in check to see. So here I'm checking to see, is this coordinate to the left of me or to the right of me, and then I move that direction. So I will stop the game and we will run it one more time. When I press play, you can actually see it doing the depth first search. And what's cool about this is because it's looking all the way to the end of the board every single time, you can this algorithm will never run into a situation where it can get boxed in, because it's looking as far as it can into the future. In fact, one of the things you can do is if you keep pressing the plus key, you can make it go as fast as you want. And I've run this for several hours. Like, the car never can crash, because again, it's looking far into the future and making sure that it never gets boxed in. What is interesting though about it is that even though it is driving and solving this problem, it's not really being that intelligent of a driver, right? It always seems to want to be in the leftmost lane. And that's one of the dangers when you do a search through a tree, is that if you look for the first available answer, which is what the depth first search does, it doesn't necessarily guarantee that the end result is a particularly awesome driver. It just ends up being one that works. And depending on the problem, that could be good enough, but if you're trying to make something that's really natural looking, it might not be sufficient. Right? So, in our situation, in our game, we only had 3 decisions per turn, but that tree ended up being pretty big, right? It ended up being a pretty complicated tree. This is actually one of the simplest search trees I've ever seen. Most games have a huge search space, so in a game of chess, on average, a player has about 35 to 50 possible moves that they could make in a given turn. Right? And then real-time games, if you're playing Call of Duty, it's a near infinite number of actions you could take, because it's not just enough to decide that if you want to move, it's move here, move to this X coordinate, or this X coordinate, or this X coordinate. If you're going to attack, which player you going to attack, there's literally an uncountable number of possible decisions that you can make. So how do we actually work in these types of environments, like real games where they get really, really complicated? Well, there's a bunch of techniques. One method is, the simple one, is just to kind of ignore some decisions. So let's say, for example, we had a search tree where we have our current state. We have all these states, and it's too much to look at. Okay, one decision is just to say, okay, I'll just ignore some of them and I'll only look at a random number of them. This is called a Monte Carlo approach, and it's pretty effective because it produces AI that behave differently every time you play the game, so it kind of gives the player a little bit of, it doesn't feel like he's playing against a machine, it feels like he's playing against something that's a little unpredictable. Another technique is we can come up with a way to estimate the goodness of a state without having to look at the levels, and that brings us into what we're calling heuristics. So a heuristic is a methodology, you can think of it as like a formula, for estimating how good a state is without having to look at the entire search tree. So it gives us a way to compare game states to each other, and it allows us to estimate the outcome of a decision without having to expand and search through the entire tree. So here, for example, let's say that my heuristic is just look ahead and tell me how many spaces ahead are clear. So if I look, directly ahead, 0 spaces. If I look to my left, it's 2 spaces, and if I look to my right, it's 3 spaces. Okay, and I'll just pick the lane that has the most spaces, clear up ahead. And if I do that, I can actually end up with a fairly intelligent AI. So let's go ahead and implement that pretty quickly here. So I'm going to say if calculate heuristic So in this particular example, what I'm doing is I'm saying calculate the, here we go. We're going to calculate the heuristic to the left of the car, and if it's bigger than what you currently are in the center, and then if you calculate the heuristic to the left and it's still bigger to what's to the right, then move left. The alternative to that is if the right is bigger than the center and the right is bigger than the left, then we would move right. And just with these two rules, and then otherwise do nothing. So we're going to look to the left, the center, and the right. We're going to say, I'm going to pick the one with the most free spaces ahead. And if I was to press play on that, alright, so if you were to press play on that, what you would see is that it's actually fairly intelligent. It will move way in advance and it'll try to stay in the clearest lane. And if I was to press play here, it actually does a pretty good job of showing you, of driving through all of this. And you can actually see it do it fairly well, right? And if we were to fast forward time for a long time, we'd eventually see that it's a great idea and it works it's fairly robust, but it still ends up getting boxed from time to time. And that brings up the important part about heuristics, is that there's two challenges. One is coming up with a good heuristic, and sometimes that just requires some trial and error and experimenting. It's not always easy to figure out what makes a game state good. So here in Spy Hunter, it might make sense to go to clear lanes, but maybe that's not the best heuristic. And heuristics are not always guaranteed to lead to an optimal outcome. And by that I mean that, as we just saw, if we have a good heuristic, it'll work most of the time, but every now and then it'll get tripped up. So why do games get their own lesson? Well, games are an interesting application of artificial intelligence for several reasons. First and foremost, they're intended to be entertaining, but not necessarily optimal. So for example, in the slide deck that you're going to be able to download, I have a link here so you can play a perfect checkers AI. It can always win. So from a research perspective, that's cool, but it's not exactly fun, right? The expectation from players is that an AI for a game is challenging yet fun. That means it has to make mistakes from time to time. It means it has to pass the Turing test. Games are also interesting because they're difficult to pre-train. right? When the developer is building the game is constantly changing, so it's hard to build an AI before the game's complete. But more importantly, before the game's released, there's not a lot of opportunities to test it against real users. So developers basically have to play the game themselves and play against the AI, which means sometimes there are good AIs and sometimes there are bad AIs as a result. But perhaps the most interesting challenge of game AI is that they usually run within very strict time constraints. So in a game like Call of Duty, you have 16 milliseconds to draw every frame of animation, and if you take longer than that, the game slows down. So most of that time is allocated to the graphics, right? Because that's what sells. But AI is only going to get 2 or 3 milliseconds. So one of the challenges in building game AI is how do you do these huge searches? How do you consider all these decisions within 2 milliseconds, right? And again, as you all saw during PEX 2, it's very easy to write code that is, short, but takes a long time to compute. So with AI, there's a lot of challenges. That's why we have to use stuff like heuristics, or maybe like a limited breadth first search, where we only look 1 or 2 or 3 moves ahead. Or maybe we only do the depth first search, where we only find the first possible solution. These are all shortcuts that we are developing so that we can try to do it within a short amount of time. And real-time systems in the world, they tend to have the same limitations as games. So when we study games, we're actually talking about how do we do real-time systems. So you survived, right? We've talked about the sense, think, act cycle. That's how we take an AI and we go through the process of determining what action it needs to perform and then actually doing it in the world. We talked about decision trees, finite state machines, and search trees. And we went through terms of like a game state, which is again like a snapshot of your game, a heuristic, which is a way to estimate the goodness of a decision or a game state. And then we explained the difference between depth first and breadth first search. So again, breadth first, we looked one layer of our search tree at the time. Depth first, we went all the way down the path. And both of them eventually will look through the entire tree, but depending upon the problem you're solving, one may be more ideal than the other, or one might be more practical than the other. And finally, we built a number of AIs. You're going to have to turn in the Pong and the Spy Hunter AIs, so I hope you saved the code for that. Thank you very much for paying attention. I hope you enjoyed this lesson. This was perhaps my favorite lesson of the entire course. So take care, have fun, keep coding, do your homework. All right, bye!